Hi, welcome to one more video on memories. So in the last video, we were discussing about having the development or understanding the memory locations, and then how do we access the different memory locations. So we were considering 1 million words. So as I said, okay, 1 million, we may not have exactly 10 lakh because we are looking at always 2 to the power of n number. So close to 1 million would be, so 2 to the power of 20, which results to 10,48,576, which is close to 1 million locations. And of course, we know that we are considering words of 8-bit, which is a byte. So you're going to have these many number of rows, and then you're going to end up with only 8 column, so that you can able to access any of the word out of that 1 million number. But if you can see here, suppose if you want to locate a particular bit, so you may have to search through the entire number of these many 10 lakh 10 lakh number of rows, so which is not a good idea to just access any particular bit for either reading or writing to that particular bit. So that's why it is always preferred to have a memory which has got an aspect ratio of very close to 1. Need not be exactly 1 all the time, so close to 1. It can be 1, 2, 3, 4, something like that. But here you can see the aspect ratio of this type of memory, where you have these many number of rows, and then and you have hardly 8 columns. So 8 columns is nothing but 8 bits here. So that, of course, as we discussed in the previous video, we're going to have the aspect ratio, which is such a huge number, which is 1,31,072 is the aspect ratio, where we are looking at less than 10 as an aspect ratio. So instead of having 20 address lines to locate each and every row, and then instead of having only 8 columns, we can certainly split this 2 power 20 number of address lines to 2 power 12 and 2 power 8, which exactly happens to be the same number of 2 power 20. So let us consider, so these many number of rows. Now the number of rows are now, so you can just think of, there's a decoder which will account for 0 to 11 number of address lines on the row side. And of course, now I have a memory which is not 1 lakh, 10 lakh 48,000. It's not of 10 lakh. Now instead of 10 lakh, so it will be now, it is 2 to the power of 12. So 2 to the power of 12 happens to be, suppose if I just find out, it is 2 to the power of 12 is 4096 rows. So where is 10 lakh rows, and how about this only 4000 rows? Now you can start from 0th row up to 4095th row. So this happens to be the number of rows here. And let us have 2 power 8. Now we know that each word is of 8 bit. So what we can think of having is, you can have this is, each one is of 8 bit. Like such, you have 0 to 255 such bits, such number of bits. Now what we have now is, so we have 0 to 4095 as the number of rows. The number of columns happens to be, now suppose if you try to multiply, now this will be 256 into 8. So this will be the number of columns now. So because this 8 is corresponding to each of the bits of a particular byte, and this 256 is the whole number. So of course, if you can see the number of address lines, are 12 here, which is corresponding to 0 to 4095, and you can have the what is this? This is column address lines. This is column address lines, which is of, because 256 corresponds to 2 power 8. Now you have, this is now you can just think of, this is from 12 to 20. So if you can ultimately see the number of address lines, which includes the row addressing as well as the column addressing, this now exactly happens to be 20 only. So I can see it is now 0 to 11 is the row addressing, and then you have the column addressing which is 12 to 20. So sorry, 12 to 19. So this is 12 to 19 because totally now you are supposed to have 20 address lines. 20 address lines are there as it is. Of course, all these, this is locating a particular byte. So once you identify a byte, now you can just read and write those 8 bits of that particular word. Suppose if you want to access a particular word, assume that you want to access a word which is the 8th row, and then maybe assume that you want to access the 15th column. If you are looking for 8th row, then you can just think of having the address as 001000. Since you are looking for the 15th column, you can just think of this as your, so out of 20 bits, if you are considering the first 12 bits, or sorry, first 12 bits happens to be for the row, you can just think of having 0001, and then you can have it as 0000. So this is now 8, this is now 12. So this is the address for this particular row, which is there in the 8th position, and if you are looking for this particular column which is there in the 15th, column, then because this is hardly 12 bits out of 20. Next, what you have is the first. Now you can write it as 1111, and then you can write it as 00, because you have to write totally. You can see now this is 12 out of 20, and here it is 8 out of 20. So totally now you have the address for locating this 8th, a particular byte which is there in the 8th row and 15th column. Now it's a complete word of 8 bits. So you may have to put an address something like this. So if you are actually putting this address, these values of zeros and ones onto this row address and these values onto the column address, you'll be exactly locating to this byte. So to this byte you can able to either read or write 8 bits of data. Now if you can actually see the aspect ratio of this, it is not so huge as it was there in this case. The aspect ratio here in this case was, okay, 2 power 20 is the number of height, that is the number of row lines. The number of column lines for each of the per bit was 2 power 3. Now it was coming out to be this much. Now if you come to this newly reformed architecture, on the row side you have 2 power 12, on the column side you have 2 power 8 as well as 2 power 3. So 2 power, now it is 2 power 12 divided by 2 power 11, which if you can actually find the aspect ratio of this one, it is not so huge as it was there in this case. So let us try to find out what is the aspect ratio of this. 2 power 12 divided by 2 power 11. If you can see, the aspect ratio is hardly 2. Because which is very clear. Suppose if you just take out this will become 2. The aspect ratio is hardly 2. So this way, instead of having all the memory locations put on the row side, we can able to certainly improvise that architecture by having the number of by splitting the address to column address and row address. We can able to split it and make the memory look like a having an aspect ratio of close to 1, because which is not always true. Now you can see you have an aspect ratio of 2, which is far better when compared to an aspect ratio of 1,31,072 when you are not splitting your address. Now this is an example for 20 bit address where you have almost close to 1 million words. Now this way we can able to split the addresses so that we can able to easily access any particular location. So let us now move on to exactly how do we store the data onto a particular, assume that you want to store 0 or you want to store 1 onto a particular memory location. How do we do that? So of course we were certainly discussing, suppose if you want to now assume that now this is the 8th row and 15th column location, which is a word which actually corresponds to 8 bits of data. 8 bits of data. Now if you want to identify this particular word, so there should be a word line which will identify, okay, this is the word what you are accessing, and you are supposed to have a bit line to access that particular bit. So you have two things now. One is word line, which word you are referring to, and in that word you have a particular bit, which bit you want to read. So you have to have two distinct signals. One is word line identifying which word, and the bit line will actually get to know what is the value of that bit that you are supposed to read. So word line will actually indicate what is to be written. Bit line will actually indicate, okay, what is to be read, what is the actual value that is stored you can able to read from this bit line. So bit lines and word lines are word lines are used to write the data, bit lines are used to take out the data from that particular bit. So let us try to understand all these word line, bit line when we actually go to uh, realization of the memories in the actual sense. So assume that I want to store a value of 0 onto a particular bit, and I want to write that value and I want to read that value. So assume that you have a word line. So there's a word line where I can able to write it, and let us assume that this is my bit line. Suppose assume that this bit line is always grounded. This bit line is always grounded. If this bit line is always grounded, suppose if this, okay, now assume that you don't have a, of course if you can see here, there is no connection between this word line and bit line. It is simply running one over the other. So if you actually read from this particular bit line, so this bit line value, read value will be equal to 0. Suppose if you want to store a 0 onto this particular bit, so you have to have this type of physical connection. So there is a word line which is running here, there is a bit line which is grounded. So if you read this particular bit, it will be reading actually 0. So assume that if at all if you want to store a 1 onto that, so the physical connection, this is a ROM connection where you'll be doing it. Now I'll just, okay, what I'll do is I'll put a resistor and then ground it. Now let me assume that I'll put a diode and then put it here. This is my word line, this is my bit line. Now we can see I have a resistor here, I have a resistor. Suppose if you want to store a value of 1 onto this bit line, if you make this word line equal to 1, if you make this word line equal to 1, you can see this word line which is connected to this diode. Let me just show that, okay, there is a connection here, there is a connection here. So since this anode of the diode is connected to word line, and the cathode is connected to bit line, and it is in turn connected to resistor which is grounded. So when I say word line is equal to 1 means, okay, you have applied 5 volt to this particular line. So because of that 5 volt, this diode is forward biased. You will get almost equal to 5 volt in ideal sense, or you're going to get almost equal to 4.3 volt, which is a minus the diode drop of this. Suppose if you read the value of this bit line, now how much is the value that you're reading? Because the voltage that you're reading on this bit line is the voltage here, which is equal to 4.3. Now this 4.3 corresponds to a logic high. But here, if you make this word line equal to 0 or 1, since there is no physical connection, there is no shorting between the word line and the bit line, the value that is read will be always 0. If at all, if you want to store a value of high onto this bit line, you have to put a diode between the word line and the bit line, so that whenever you make the word line equal to 1, the read value on this particular bit will be equal to 1. So this is one such possibility of storing a 0 or 1 onto a particular bit. So instead of using a diode, we can also think of using a MOSFET to realize the same bit 0 and bit 1 realization. Again, for storing 0, so there is nothing to be fabricated between the word line and the bit line. This is the indication of 0. That is, if you want to store a 0 onto that, no need to fabricate any MOSFET or MOSFET over here. Suppose if you want to store a 1 now, so let us just consider you have this word line, you have this bit line. So this is now you can just think of having a connection like this. So this is connected here, this is now VDD. Now we connect, this is word line. Now if you can see here, this word line is connected to gate. Whenever this word line is equal to 1, this MOSFET turns on. Whenever this MOSFET turns on, you'll get the VDD voltage coming over here. So the value that is stored in the bit line, the value that is read from the bit line, will be equal to high. Meaning, if at all, if you want to store a logic high onto a particular bit, so there should be a transistor that should be fabricated between, of course there should be a MOSFET with its gate connected to word line and the drain is connected to VDD and the source will be connected to the bit line point. So this is how you can able to store a 1 with the help of a diode, with the help of a MOSFET. So because you have a pull down transistor, which is going to happen like this. Suppose if you just think of having a slightly different configuration, assume that I have a resistor here, this is my bit line, this is equal to VDD, you have a word line. Since you have a word line, if you can see here, the voltage that is read from this bit line is always high. You can see what the voltage that you are connected here, it is VDD. Since nothing is coming over here, since there is no connection, the same VDD will come over here because the drop is almost 0. If at all if you want to have a bit 0 to be stored with this type of pull-up resistor, you can just think of having, okay, you just run it through this and then you have your word line. This you can ground it. This is also, this is connected to VDD and this is your bit line. Now if you actually see the configuration, suppose if this word line is equal to 0, if this word line is equal to 0, what you are getting is logic high. So here if this word line becomes 1, so whenever this is equal to 1, the current flows through this and it will be get grounded. You're going to have maximum drop happening here. The voltage that is coming over here in this bit line equal to is 0. Meaning, in case of pull-up resistor used in your memory, if you want to represent a high, no need to connect any transistor. You can see now you have a pull-up resistor or pull-up. If there is a R pull-up connected in this type of configuration, if word line is equal to 1, what are the value that is stored here? Because there is no physical connection, the value that is stored in this particular bit upon reading the bit line value is equal to VDD. Now we consider there is a transistor, there is a MOSFET which is connected in this configuration with the source grounded, drain connected to this resistor point. Whenever the word line is equal to 1, whenever the word line is equal to high, this transistor turns on. When this transistor turns on, the entire voltage will drop across here. The bit line voltage will be equal to 0. Meaning it is exactly it's exactly opposite to that of a pull down configuration, where in this pull down configuration you have a MOSFET to represent a you have a MOSFET to store a bit line to store in a particular bit high value. If you don't want to store, if you want to store a 0 value, you're not having a transistor. But it is exactly the opposite case in case of a pull-up resistor. If you are having a pull-up resistor, if you have a transistor, then the bit value, the value that is stored in that bit is low. If you don't have a transistor, the bit value that is stored in that particular bit will be equal to high. So this way we can able to permanently store the value of either 0 or 1 onto a particular bit. So that's why this is called as ROM. So assume that you have n number of, so assume that I have n number of bits. Okay, this is my let me consider, this is my pull down logic. This is connected to ground. Let me consider this is BL0, this is bit line 1, bit line 2, this is bit line 3. I have word lines, this is word line 0, this is word line 1, this is word line 2, this is word line 3. I have 3 word lines, I have 3 bit lines. Assume that of course here you can able to store 16 different bits, and of course you have a pull down resistor. Suppose if there is no diode or the MOSFET being connected between any of the word line to any of the bit line, whenever you try to read the values from each of the bit line, the red value will be equal to always 0, because it is 0 0 0 0. Whenever you read the value of this, of course you make sure that okay, bit line is equal, sorry, word line is equal to 1 1 1 1. When the word lines are made equal to 1, if you want to see what is the value that is stored in these 16 bits of this particular memory, so it is says that 0 is stored in this all 16 bits. So how do you read the first 4 bits of this memory? You make this one read the value. When I make this one read the value, I know that I'll be getting 0 0 0. 0 will be on the bit line. If you want to know what is the value that is stored in these 4 bits, make this one and then try to read this value. So this is also, of course, you'll be reading 0 0 0 0 0 0, and then all the 16 locations are ending with zeros. Now assume that if you put a diode here, so or if you put a MOSFET, so what I'll do, I will connect a VDD line here. I will connect, so let me have a red line to represent VDD, or let me just have this line which is representing VDD. So let us try to connect a MOSFET. So this is a MOSFET. Let me try to connect let me connect one more such MOSFET here. See now, okay, let me have one more. Okay, I will have, this is one more VDD line. Let me have one more transistor connected from this to this, and then let me have more transistor connected from this word line. You can see I'm just connecting from this word line to this bit line. Assume that this is the transistors connected at different points. Let us try to understand. Of course, when there was no transistor connected to any of the cross bit line and word line, the value read from all 16 bits was 0 0 0. So all 16 bits were 0. Now what we have, we actually have transistor number 1, 2, 3, 4 have been fabricated at appropriate positions. Let us try to read what is the value that is stored in all 16 different bits, Now if I want to know what is the bit that is stored in this particular row of all the 4 bits, you make this word line is equal to word line 0 is equal to 1. When I make this word line 0 is equal to 1, the value that is stored here, you can see now, when you make this equal to 1, will you be getting VDD over here? What is this? Here it would be 0 1 0 0. When you make this word line equal to, when you make this is with word line 0 equal to high. If you make this word line 1 equal to high, we'll get 0 0 0 and this will be 1, 0 0 0 and 1. And if you make this 1, if you make this word line 2 as 1, you can see this word line is not actually driving. Okay, now this is not at all driving any, of course. What I did, one thing wrong here is, so let me just rewrite this. So let me just connect it somewhere here, because what should happen is we should go to this. Let me connect it from here. This is one small mistake. Let me just take out this. See now, this is VDD, this is connected here. If this okay, how about this? Let me just change this also. Let me connect. Okay, let me just do it like this. Okay, this is perfect, because the gate should be always connected to the word line. So here the mistake what I made was the VDD was connected to gate, which was always on, which should not be correct. Now VDD is always connected to drain. Here you can see the VDD, this is actually drain, source, this is now source, drain, this is now, this is drain, source, drain, because source is always at a lower potential. You can see this is source which is at a lower potential, this is drain connected to VDD, and again this is source, this is drain. I hope you got this mistake. So the gates are always driven by the word lines. You can see this is your word line which is driving the gate. Now this is fine. Suppose if you make this word line 2 as high, so I will going to certainly get this bit as 1, and this is 0, this is 0, and then this again 0. If you make this is word line 1, this is word line 2, this is word line 3. If word line 3 is 1, you're going to get it as, of course you don't have any MOSFET here, 0, don't have any MOSFET here. This is second one, this is the third one, sorry, third one you have a MOSFET, this is 0. So this is bit line 0, bit line 1, bit line 2, bit line 3. So out of 16 bits, the value that is stored in different bits is 0 1 0 0 0 0 0 1 1 0 0 and this. So this is the value that is stored in different 16 bits. So now it is put in an array form so that you can be able to easily read the value of all these bits. Suppose if you make all the word lines as 111, if you make all the word lines as 111, so what you'll be reading from your bit line would be 1111. So this will be the value of the bit lines that is 0 to 1. If you make all word lines as 1, if you make this one, make this one 1 1 2 1 and W3 also 1, if you make all the 4 bit lines or all the 4 word lines as 111, the bit lines that are read from 0 to 3 would be equal to 1111. Assume that in this configuration, if I make something like this configuration, let me just say if I make one more transistor here which can go this way. See now this is an extra transistor that has been added here. This is extra. Let me add one more here. Maybe let me just add that over here. So these are the two extra transistors that are added. You can see the difference now. Suppose if you add this transistor and this transistor extra, what will be the individual readings? Now it would be 0 1 1 0. That is because you have a MOSFET here, so the bit that is stored in this bit line is equal to 1 when the word line 0 is equal to 1. In the other case it is 0 1 0 1, and then you have 1 0 0 0, and then it is 0 0 1 0. So this is the value of individual bit lines, that is bit 0, bit 1, bit 2, bit 3, when the word lines individually, word line 0 is 1, word line 1 is 1, word line 2 is 1, word line 3 is 1. Suppose if you make all the word lines as 111, so what I'll end up with is, this is 1, this is 1, this is 1, this is also 1. You can see this type of configuration is called as OR configuration, because whether you have this or this, one of them is sufficient to get a bit line of 1 when all the word lines are 111. I'll just repeat. If you want to get a particular bit line to be 1 with all the word lines as 111, it is necessary to have only one transistor in any of the bit position. If you have only one, then you can able to get that particular bit line as of high value if all the word lines are becoming 111. So that's why it is called as OR configuration of a ROM. So this is 4:4 or ROM configuration. So we'll see in the next video, okay, how do we do different type of other ROM configurations.